Hello, I'm discussing about Gibbs adsorption equation, adsorption at surface of liquids. Surface tension is a force per unit length or surface free energy per unit area. A dissolved solute may increase or decrease the surface tension of the solvent. If a solute brings about a decrease of surface tension, then it has a tendency to accumulate more at the surface of the liquid. Since they may, the surface tension of the liquid or surface free energy per unit area of the surface is decreased. This type of behavior is called positive adsorption, or the solute is said to be exhibit positive surface activity Cs greater than Cv, higher at the surface of the adsorbent for the solute Cs than in the bulk solution Cv. If the solute brings about an increase of surface tension, then its concentration at the surface of the liquid. Since this way, the surface tension of the solution is found to be less than in the bulk of solution. This type of behavior is called negative adsorption, or the solute is said to exhibit negative surface activity Cv greater than Cs. A quantitative expression which relates the extent of adsorption and the change in surface tension of the solvent due to addition of the solute was derived by J.W. Gibbs is known as Gibbs adsorption equation. Let N1 and N2 are the number of moles of solvent and solute respectively at the surface mu1 and mu2 be the chemical potential of solvent and solute respectively. G equal to N1 mu1 plus N2 mu2. Let gamma be the surface tension and S be the surface area, surface free energy equal to gamma S, so that G equal to G equal to N1 mu1 plus N2 mu2 plus gamma S, equation 2. Differentiating equation 2, dg equal to n1 d mu1 plus n2 d mu2 plus mu1 dn1 plus mu2 dn2 plus gamma ds plus s d gamma. Free energy obtained from G equal to F Tp n1 n2s function of temperature, pressure, composition, n1 n2 and surface area. So dg equal to dg over dava g over dava t dt p n1 n2s dt plus dava g over dava p dt t n1 n2s dp plus dava g dava n1 dt t p n2 s dn1 plus dava g over dava n2 dt tp n1 s dn2 plus dava g over dava s dt tp n1 n2 ds. Dava g over dava t dt p n1 n2 s equal to minus s surface area. Dava g over dava p dt t n1 n2 s equal to b volume. Dava g over dava n1 dt Tp n2s equal to mu1 chemical potential of solvent. Dava g over dava n2 dt Tp n1s mu2 chemical potential of solute. Dava g over dava s dt Tp n1 n2 equal to gamma surface tension. Substituting the value of mu1, mu2, sb, gamma in equation 4, dg equal to minus sdt plus bdp plus mu1 dn1 plus mu2 dn2 plus gamma ds equation 5. Mu1 dn1 plus mu2 dn2 plus gamma ds is similar in equation 3. So that rest of the part is equal comparing the equation 3 and 5 minus sdt plus bdp equal to n1 d mu1 plus n2 d mu2 plus gamma ds. Question 6. At constant t and p dt equal to 0, dp equal to 0. So n1 d mu1 plus n2 d mu2 plus gamma ds equal to 0. Equation 7. Suppose system under consideration is divided into two parts, surface phase part under the influence of surface forces, bulk phase, that is the remainder of the solution. For bulk phase, surface consideration are not involved. N1 naught, N2 naught equal to number of moles of the solvent and solute respectively in bulk phase. N1 naught dmu1 plus N2 naught dmu2 equal to 0. Equation 8. Equation 8 is multiplied by N1 over N1 naught, N1 dmu1 plus N2 naught, N1 over N1 naught dmu2 equal to 0. N1 dmu1 equal to minus N2 naught, N1 over N1 naught dmu2. Equation 9. Substituting value of N1 dmu1 in equation 7 minus N2 naught, N1 over N1 naught dmu2 plus N2 dmu2 plus gamma d is equal to 0. Taking common dmu2, N2 minus N2 naught, N1 over N1 naught plus gamma d is equal to 0. N2 minus N2 naught, N1 over N1 naught dmu2 equal to minus gamma ds. So minus gamma ds over dmu2 equal to N2 minus N2 naught N1 over N1 naught minus d gamma over d mu2 equal to 1 over s N2 minus N1 N2 naught over N1 naught. Equation 9. N2 minus N1 N2 naught over N1 naught equal to excess concentration of solute in the surface phase. 1 over S N2 minus N1 N2 naught over N1 naught excess concentration of solute in the surface area of the surface. Let S2 be the excess concentration of solute in the surface phase per unit area, so that S2 equal to minus d gamma over d mu2 and S1 be the excess concentration of solvent, S1 equal to minus d gamma over d mu1. We know that mu1 equal to mu2 naught plus RT ln A2, mu2 naught, mu naught 2 equal to standard chemical potential constant, A2 activity of solute. Differentiating d mu2 equal to RT d ln A2, so that S2 equal to minus d gamma over RT d ln A2. S2 equal to minus 1 over RT d gamma d ln A2, d ln 2 equal to 1 over A2 dA2. Substituting the value of d ln A2 in the above equation, we get S2 equal to minus 1 over RT d gamma 1 over A2 dA2. So S2 equal to minus A2 RT, rearranging d gamma dA2. For dilute solution A2 equal to C2, A2 equal to activity, C2 concentration, so that S2 equal to minus C2 over RT, d gamma dC2, S1 equal to minus C2 over RT, d gamma dC1. S equal to C over RT, d gamma dC. These are the forms of Gibbs adsorption equation. If d gamma dC equal to negative, S is positive, it means that by positive absorption in the solute would tend to accumulate on the surface. If d gamma over dC equal to positive, S is negative, that is the concentration of the solute on the surface is less than in the bulk of the solution. This is the case of negative adsorption. This is sometimes called desorption. Substances like soap, sulfuric acid, sulfonates, alcohols, and detergents lower the surface tension of the water and hence show positive adsorption. These are called surface active agents. Strong electrolytes and aminous benzoic acid increases the surface tension of water and hence show negative adsorption. Okay. Below, it's all about Gibbs adsorption equation, adsorption at the surface liquid. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That is now. Bye bye. See you again.